Meteors have the power to transform our planet, to wipe out huge swaths of life on Earth in one impact. But not all are that dramatic. We are hit by more than 100 tons of small, sand-sized particles every day, and they are essentially unnoticeable. About once a year, a car-sized meteor comes crashing through our atmosphere, but the resultant, impressive, fiery streak burns up long before hitting the ground. It's only on the scale of millions of years that we are in danger of being hit by meteors a kilometer or two wide, big enough to do some serious damage. But we've not seen one of those since the dinosaurs. Lucky for us. But size isn't everything. In fact, the biggest impacts may not even be from the largest objects. If one particularly interesting theory is true, some very rare meteors may be made of something a little more exotic than rock. Externally, there would be not much to differentiate these rarer meteors. In the vacuum of space, they would appear exactly the same as any other space rock. But while regular meteors might create a fiery streak in the sky, these outliers would have impacts that exceed the largest of nuclear bombs. And those are just the small ones. If a kilometer-sized meteor of this variety hit the Earth, similar in size to the normal meteor that killed the dinosaurs, we might not have a planet anymore. That is the power of a meteor made of antimatter. Could antimatter meteors really exist? What clues would help us identify them from regular matter meteors? And how big would they have to be to become a major problem? I'm Alex McColgan, and you're watching Astrum. Join me today as we test the scientific theory behind antimatter meteors and explore the odds of such objects lurking in our solar system.
Antimatter is a funny substance. The fact that it exists means that we shouldn't be here.
It is almost identical to regular matter, with a few key differences. One is that it has an inverted charge. Another is that when antimatter meets regular matter, the two annihilate each other completely, converting almost entirely into energy.
Now, in the early universe, it wasn't just matter that was created. In theory, an equal amount of antimatter came into being too.
All the matter should have bumped into the antimatter, and everything would have cancelled each other out. This would have left no universe for us, as there would be nothing to make the universe out of. It is one of the mysteries of science that this did not happen, and for some reason a slightly larger amount of matter coalesced into existence than antimatter, perhaps as small a discrepancy as 1,000,001,000 matter particles to every billion antimatter ones. Scientists are still trying to figure out why this might have occurred, but the mystery remains unsolved for now. Perhaps there is some rule at play that we've not yet identified. Whatever caused it, this imbalance is the reason the universe we see around us is almost entirely made of regular matter, and the only place we reliably see antimatter is when they make tiny amounts of it in experiments at CERN and in other particle accelerators. Some hospitals even have small particle accelerators to create positrons for PET, or positron emission tomography scans. However, just because we don't see it doesn't mean that tiny pockets of antimatter couldn't exist. When the raw, primordial soup, quark, gluon plasma of the Big Bang began to form into particles, while overall there would have been more matter than antimatter, in local areas there were fluctuations. So it's logical that clumps of antimatter could have emerged and dominated as gravity pulled them together. After all, if you flip a coin enough times, you'll inevitably end up with runs where you flip nothing but heads or nothing but tails. If these clumps were large enough in scale, they wouldn't annihilate away in a burgeoning solar system. Instead, they would be the solar system, and it would be pockets of matter that would eventually annihilate out, leaving behind stars and protoplanetary disks made entirely of antimatter. This seems highly theoretical, But could such solar systems actually exist? For the most part, an antistar would be visually identical to a regular one, as antimatter behaves in all the ways you might expect matter to. It obeys the same laws of gravity, and mostly looks the same. The only telltale giveaway would be when regular matter interacted with it, such as when the interstellar winds met the edge of the fledgling solar system, and resulting annihilations would emit gamma radiation. And curiously, there are some systems that seem to do this. 14 such gamma-ray emitting star candidates were found in the Milky Way thanks to the Fermi Large Area Telescope in 2021. If these are antistars, and their profiles do match what we would expect out of antistars, so this is not ruled out, and they're not other objects that emit gamma rays like pulsars or black holes, then systems made of antimatter with planets and asteroids do exist. The ratio of antistars to stars would be about 1 in 400,000. So the stage is set. If antistar systems could exist, it's not illogical to think that antimatter meteors do too. And that leads us to the question, what are the chances of them coming to Earth? The idea of antimatter meteors striking our planet is not a new one. Even back in 1940, only a decade or so after the discovery of antimatter as a concept, Russian-American physicist Vladimir Rozhansky began to speculate about their existence. All it would take was for our solar system to have passed one of these antimatter solar systems at some point in the past. The sun's gravity would then knock a few outlying antimatter meteors out of their precarious orbits and into ours. Antimatter meteors may not have been able to form in our solar system. Their particles would have been annihilated by interaction with matter far too early for that. But in space, just an empty vacuum somewhat devoid of matter, there would be nothing for them to annihilate with. So there's a chance they could be among us. And if they were, would we even notice? Soon after Rozhansky, American astronomer Lincoln LaPaz began to wonder whether any of the craters on Earth could be attributed to antimatter meteors. So perhaps this is the time to consider what an antimatter meteor could do if it came in contact with the Earth, so we know what to look out for. Thankfully, it's not necessarily a simple journey. The first issue such an antimatter meteor would encounter before reaching Earth would be our atmosphere. To be fair, this is a problem for regular meteors too. When one of those trades vacuum for air, the speed at which it's traveling causes it to generate incredible friction, causing some or all of the meteor to burn up on the way down, depending on its starting size, leading to the fiery streak I mentioned at the start. However, antimatter meteors would have it much worse. Each particle of atmosphere that the antimatter meteor encountered on the way down would annihilate a similar amount of the meteor. So to understand what happens next, we need to turn to Einstein's famous equation, E = mc squared. The meteor's mass, multiplied by the speed of light squared, tells us how much energy would be released by the meteor on the way down. Technically, twice that, as for each particle of the meteor that's annihilating, a particle of atmosphere is doing so too. This is potentially a huge amount of energy being released. Let's do a bit of a thought experiment to work out how much. While the dividing line between the atmosphere and space is either 100 kilometers up if you're talking to Europeans, or 80 kilometers up if you're talking to Americans, as the two haven't reached a consensus on that point yet, over 90% of the mass of Earth's atmosphere is actually clumped below 16 kilometers, clinging to the planet as closely as possible thanks to the pull of gravity. So by working out how much air exists between this line and the Earth's surface, we can get a rough idea of how much antimatter you'd need to have before an antimatter meteor hits the ground. This is a little tricky to calculate, but thanks to a chart released by the International Standardization Organization, I was able to add up the sum total of the atmosphere at different elevations between the surface and 20 kilometers high, and found that in a 1 meter by 1 meter corridor between space and the surface, you'd have roughly 10,132 kilograms worth of atmosphere. A meteor would need to be roughly this large to even hit the surface, assuming it traveled the most direct route straight down. Now, antimatter is similar in mass to matter, so we can assume that they would have comparable compositions too. Most meteors are made of chondrites, so assuming an average antimatter meteor made of the antimatter version of the same stuff, we can put the density of our antimatter meteor at around 3,400 kilograms per cubic meter. Of course, there's then a balancing act you need to do. The bigger the meteor, the larger the surface area, and the more air it thus encounters before it reaches the surface. However, as volume scales up in cubes, while surface area is only squared, there is a sweet spot you can hit where the amount of air being annihilated by the meteor would theoretically perfectly match the amount of mass the meteor possesses. And then we know that any mass of meteor above that would make it through the atmosphere to hit the ground. Using very rough maths, I found that a 3x3x3 meter meteor, or 27 cubic meters, worked best for this calculation, which had a mass of 91,800 kilograms, or 3,400 kilograms per cubic meter times 27 cubic meters. This would only encounter 91,191 kilograms worth of air on the way down, meaning 608 kilograms worth of meteor would actually hit the surface. That's approximately the mass of a large grand piano. How much damage could 600 kilograms of antimatter actually do? It's time for our equation, E equals mc squared. Using this calculation, we learn that 600 kilograms of remaining meteor releases 5.4 times 10 to the power 19 joules of energy, or 54 quintillion joules. Then double that, as the ground being annihilated releases that amount too, so 108 quintillion joules. For a point of reference, a 1 megaton nuke gives off 4.18 times 10 to the power 15 joules of energy. Even if we scaled up to the largest nuke ever detonated, the Tsar bomber, which had a yield of 50 megatons, we're still only looking at 2.09 times 10 to the power 17 joules, a full 5,000 times weaker than our antimatter grand piano. And the Tsar's bomber blast was so great, towns within 55 kilometers, like Seveny, were leveled. Wooden buildings 160 kilometers away were reportedly damaged. The light from the blast was seen 1,000 kilometers away. Windows in Norway and Finland were shattered by the explosion. If just 600 kilograms of our antimatter meteor impacted in the middle of a state like Texas, the whole state would be destroyed. The center vaporized, the rest devastated. This is just the energy release from our antimatter meteor annihilating on the ground, not even going into things like kinetic energy. But even then, it's actually not just the 600 kilograms that hits the ground we need to worry about. When you consider the rest of that 91,200 kilograms of mass that was annihilated in the atmosphere, the blast radius becomes a lot bigger. While some of that energy would travel upwards into space, minimizing the damage below, suddenly you're not just worrying about Texas. You're worrying about the entirety of the USA. All that's just from an antimatter meteor that's comparable in size to a car. We really do not want to get hit by an antimatter meteor. So what actually are the risks here? Let's say that an antimatter meteor had got swept up in the sun's gravity well millions to billions of years ago. Could it now be one of the 40,155 near-Earth asteroids that NASA tracks? The good news is no. For one simple reason. Space isn't actually empty. While we talk of space being a vacuum, even in space there are trace amounts of dust floating in the void. As such, an antimatter asteroid traveling even through the interstellar medium would not likely have a survival rate of longer than around 300 years. As we last clipped another star 70,000 years ago, Schultz's star, in case you're interested, it would have to have been an exceptionally lucky antimatter meteor to not only dodge all the other asteroids in that time, but also to have not encountered enough dust since then that it would have disintegrated into gamma radiation. For this same reason, an interstellar antimatter comet coming through our solar system would be unlikely. Small ones would burn up before reaching us, and larger masses would be noticeable. They would emit a steady stream of gamma rays as they traveled, making them detectable to our telescopes. No such sparkling asteroids have ever been detected. So, all in all, while it would be devastating to be hit by an antimatter meteor, it is unlikely that one would survive long enough to reach our planet, assuming they and antimatter stars exist in the first place. We are probably quite safe. Besides, if antimatter meteors existed, we might have seen some evidence of them before. Meteor impacts with unusual destructive capacity, but leaving no traces of the meteor that caused it. We've not seen anything like that. Have we? In June 1908, a fireball lit up the sky in a remote part of Siberia. The meteor exploded before hitting the ground, its detonation causing massive forest fires and sending trees crashing to the ground like bowling pins in an area of destruction kilometers wide. Witnesses more than 30 kilometers away reported seeing a flash brighter than the sun, followed by a roar of thunder. Due to its remoteness, scientific teams did not arrive at the site until 1927, but even then, the destruction caused by the blast was easy to see. Strangely, for an object that caused such destruction, almost no trace of the meteor was ever found, beyond a few microparticles. But the Tunguska event couldn't have been caused by an antimatter meteor, could it? Don't worry, we know that it probably wasn't an antimatter meteor, but there was a lot of debate about the topic in the past, and we couldn't resist being a little spooky. Have a look around you. Everything you see, from the skin of your hands to the screen you're watching this video on, is a different combination of the same three building blocks of matter: protons, neutrons, and electrons. Now, let's look a little farther, say at Mars, or the Andromeda Galaxy, or even halfway across the observable universe. And still, there is matter made of protons, neutrons, and electrons, as far as the eye can see. At first, this might not sound all that surprising, but for once, the mystery here isn't that we've seen something we can't explain, but rather that we haven't seen something we were expecting: a universe just as full of antimatter. I'm Alex McColgan, and you're watching Astrum. Join me today as we explore the world of antimatter and learn about its interactions with other particles and even with gravity. By the end of this video, you'll probably agree that antimatter is a bit weird, but you'll also see why some physicists are frustrated that it isn't weird enough. Let's get one thing out of the way first. Although it might sound like something straight out of science fiction, antimatter is very real. It forms a critical part of the standard model of particle physics, and particles of antimatter have been observed in experiments going back nearly a century. The very first detection of antimatter dates back to a 1932 experiment conducted by Carl D. Anderson at Caltech, using a cloud chamber immersed in a magnetic field. When charged particles from outer space, broadly called cosmic rays, intercept the Earth's orbit and fly through this chamber, the magnetic field curves their paths according to the charge and mass of each particle, and the clouds show a visible imprint of their resulting trajectories. Anderson was hoping this experiment would help determine just what kinds of particles were streaming into the Earth from the cosmos, and he may have found just a little bit more than he bargained for. What Anderson saw was that these cosmic rays included both positively and negatively charged particles. The masses of the negatively charged particles lined up exactly with the known mass of an electron. But some of the positively charged particles were far too light to be protons. Instead, they appeared to have the mass of an electron despite having the opposite charge, and so these never before seen particles came to be known as anti-electrons, or later positrons for short. In 1936, Anderson would win the Nobel Prize in Physics for this discovery. Meanwhile, a British physicist, who was also destined to win a Nobel, had been developing a description of electrons that would fit nicely within the framework of quantum field theory. His name was Paul Dirac. By 1928, Dirac had realized that in order to describe electrons as quantum fields in a way that was physically consistent with special relativity, they had to be part of a larger mathematical structure, later known as a Dirac spinner, that inevitably gave rise to both positively and negatively charged versions of the same particle. In this way, Dirac had predicted the existence of positrons before Anderson had even built the cloud chamber that would detect them 4 years later. What's even more incredible is that electrons aren't the only fundamental particle to come in a 2-for-1 Dirac spinner package. Other particles of matter, like the quarks that make up protons and neutrons, each have their own antiquark counterparts. These antiquarks can come together to form antiprotons and antineutrons, which can then bond with positrons to form anti-atoms and anti-molecules. You could make a whole planet out of antimatter, and from the outside, it would look quite similar to an ordinary planet made of ordinary matter. But if antimatter were too similar to matter, if the only difference were the sign of its charge, then it would be impossible to explain why our universe contains so much of one and so little of the other. This cosmic mystery, known as the baryonic asymmetry of the universe, sent physicists on a decades-long quest to try and find as many differences as they could between matter and antimatter. That quest lives on today, spearheaded by particle colliders at CERN that are capable of producing, trapping, and studying both positrons and antiprotons. But before we talk about these experiments, let's try to summarize what we already know about the properties of antimatter. When studying antiparticles in isolation, experiments have confirmed with ever greater precision that their intrinsic properties, namely their masses, are exactly the same as for ordinary particles. And when studying how antiparticles are affected by electromagnetic forces, experiments have again found that they behave the same exact way as ordinary particles, except with the opposite electric charge, just as Anderson had observed in his cloud chamber. But electromagnetism is just one of the 4 fundamental forces of nature, alongside gravity and the weak and strong nuclear forces. And as physicists began to better understand the weak force in the 1950s and 60s, they realized that particles and antiparticles are actually affected by it quite differently. The first surprise was that ordinary particles could only feel the weak force if they were left-handed, and antiparticles could only feel it if they were right-handed. The concept of handedness, or chirality, is subtle and difficult to conceptualize for particles with mass, but a loose analogy can be drawn with a particle's helicity, which describes whether a particle is spin up or spin down along its direction of motion. In this analogy, a spin up particle is called right-handed, while a spin down particle is called left-handed. The second, and even crazier surprise, was that right-handed antiparticles experienced a different strength of the weak force as compared to left-handed ordinary particles. In practice, this means that the quantum probabilities for radioactive decay in ordinary nuclei are somewhat different from the probabilities of the analogous decay processes in antinuclei. This fundamental asymmetry between particles and antiparticles was first observed in a 1963 experiment run by James Cronin and Val Fitch of Princeton University.
who would be awarded yet another Nobel Prize for their discovery. When this asymmetry was discovered, there was some hope that it would explain the baryonic asymmetry of the universe. Perhaps these differences in the weak force were responsible for the abundance of matter and utter lack of antimatter around us. But the maths didn't quite work out. There simply wasn't enough of a difference between the strength of the weak force acting on particles versus antiparticles. That was when physicists began to turn their attention to the strong nuclear force. Theoretical models predicted that, just like in the weak interaction, there should be some differences in how left-handed particles and right-handed particles feel the strong force. But antimatter just keeps surprising us. Every experiment to date suggests that the strong force treats particles and antiparticles just the same. This brings us to the last of the 4 fundamental forces and the subject of today's ongoing experiments at CERN, gravity. To be honest, suggesting that gravity might treat matter and antimatter differently is kind of a long shot. Think back to the popular legend of Galileo tossing stones of different sizes and materials from the Tower of Pisa. They all fell at the same rate because the gravitational acceleration on Earth is 9.8 meters per second squared, regardless of which object is falling. Of course, the experiment works even better in a vacuum chamber, where air resistance is taken out of the equation. Newton expanded on this idea and showed in the 17th century that your gravitational acceleration anywhere in space depends only on the mass of the object pulling you and your distance from it, but not on any of your personal properties, not even your own mass. This famous result, known as the equivalence principle, is the foundation of Einstein's theory of general relativity, our most accurate and successful model of gravity to date. With that in mind, physics is still an experimental science at its core, and we can't know for sure whether matter and antimatter obey the same laws of gravity unless we check for ourselves. The physicists at CERN set out to do just that, motivated not only by the baryonic asymmetry of the universe, but also by a few speculative papers suggesting that the cosmological properties of dark matter and dark energy could be more easily explained if antimatter were to have a negative gravitational charge, or, to put it simply, if antimatter were to fall up rather than down. There are several ongoing experiments at CERN testing the gravitational properties of antimatter, including Aegis, G-bar, and Alpha. Today we will focus specifically on a key experiment coming out of the Alpha group that was published in the journal Nature this past September. After decades of assumptions, this experiment has brought us real-world data on the gravitational acceleration of antimatter on Earth's surface. But before we show you the results, let's take a moment to appreciate just how intricately this experiment was designed in order to isolate and measure the effects of gravity. The first step in the experiment is to secure a beam of several million positrons per second emitted from a radioactive isotope of sodium. Most of these positrons end up colliding with ordinary matter in the experiment, causing miniature explosions in which positrons and electrons annihilate each other and release a small burst of energy in the form of light. But a small fraction of the positrons survive as they are guided through the experimental apparatus, where they are cooled by low pressure gases and trapped by electric and magnetic fields. But observing the effects of gravity on these positrons would be nearly impossible. Their masses are so small that the tiny force of gravity felt by each particle is overshadowed by even the smallest fluctuations in the surrounding electromagnetic fields. That's why this collection of positrons is merged with a separate container of antiprotons, where they bond and form neutral antihydrogen atoms that are much less responsive to stray electromagnetic fields. And where did the antiprotons come from? Suffice it to say that they were produced by firing ordinary protons into a block of metal really, really fast. Yes, physics is awesome like that. Once the anti-hydrogen atoms are created, they behave like tiny, weak magnets that can remain trapped by complicated arrangements of external magnetic fields. Now, this magnetic interaction is weak enough that it no longer overwhelms the gravitational effects that we are trying to measure. The chamber containing these anti-hydrogen atoms is nearly a vacuum. There are just about 200,000 atoms of ordinary gas per cubic centimeter, compared to a typical atmospheric density of 20 quintillion atoms per cubic centimeter. Under these conditions, the trapped anti-hydrogen atoms almost never collide or annihilate with atoms of ordinary matter. Instead, they can more or less just float around the chamber for minutes or longer. But as the magnetic fields used to vertically trap the anti-hydrogen atoms are weakened, this random floating eventually allows the anti-hydrogen atoms to escape through either the top or the bottom of the chamber, where they can collide with a wall of apparatus, annihilate with some ordinary atoms, and release a small burst of light. In the alpha experiment, this happens over the course of about 20 seconds. The theory behind the experiment is that if gravity really pulls antimatter downwards, more of the anti-hydrogen atoms escape through the bottom than the top. The stronger the gravitational force, the more atoms escape through the bottom. The simulations the alpha team ran showed that under normal gravitational attraction, about 85% of the anti-hydrogen atoms should escape through the bottom, whereas only 20% of them would escape through the bottom if gravity pulled antimatter upwards. If there were no gravitational force at all, the simulation showed a more even distribution of 55% escape through the bottom, probably only differing from 50% due to asymmetries in the experimental apparatus itself. What did the actual experiment find? Well, roughly 75% of anti-hydrogen atoms escape through the bottom of the chamber, showing a clear preference for downward pulling gravity. As any thorough scientist would, the alpha team repeated this experiment to collect a variety of data points that could tell a more complete story. They redid the procedure under various levels of magnetic field bias, which applied external upward or downward magnetic forces on the anti-hydrogen atoms. On this graph, a bias of -1g means that enough magnetic force is applied to counteract normal gravity, while a bias of +1g means that an extra g of magnetic force is applied to push the anti-hydrogen atoms downward, and so on. The team made predictions through simulations for each bias and for various possible gravitational interactions, which produced the orange, green, and purple curves shown here. As you can see, the experimental data points shown in blue best match the orange curve, which represents the normal simulation where gravity pulls antimatter downwards. But because the data falls just a bit below this curve, the best fit gravitational acceleration was only 0.75 g. 3/4 of the strength of gravity acting on ordinary matter. Does this mean that gravity affects matter and antimatter particles differently after all? Not necessarily. Let's have a look at the error bars. They indicate that there are two major forces of uncertainty in the results, including an uncertainty in the applied bias, possible errors in alignment, and other systematic and statistical uncertainties. When accounting for these uncertainties, the best fit gravitational acceleration is actually reported as 0.75 g plus or minus 0.13 g plus or minus 1.6 g. This means that a full 1 g of gravitational acceleration is still fairly consistent with the collected data. Future experiments will be able to determine more precisely how strongly gravity acts on antimatter, but we can already rule out speculative theories that rely on antimatter falling up instead of down. In the end, despite how weird and backwards the world of antimatter is, it seems that only the weak force actually applies differently to particles and antiparticles. But explaining the baryonic asymmetry of the universe would require much more drastic differences between the two. So scientists aren't done looking for them. Could there be new forces and particles that interact even more weirdly with antimatter? Or would you be willing to accept that having so much more matter than antimatter around us is a mere coincidence? In any case, let us know if you've learned something new about antimatter from watching this video, and whether this is a topic you'd like to hear more on.
800 light years away, there's an unseen antimatter factory churning out high-energy positrons. Tiny particles of antimatter that are streaming through the cosmos and colliding with our planet. For much of history, we didn't know this strange source existed. Most of the positrons bombarding us went completely undetected, instead getting absorbed in our planet's atmosphere. It wasn't until we started looking from beyond the bounds of our planet that we noticed them. In 2011, NASA's Alpha Magnetic Spectrometer, a state-of-the-art particle detector some 200 miles up aboard the International Space Station, was switched on. What did it find? You guessed it, positrons. The presence of these subatomic particles was to be expected, but not in the numbers they were finding. Such was the sheer volume of positrons being detected that the usual sources like natural radioactive decay and cosmic rays no longer offered a sufficient explanation. So, where were they coming from? We've only recently been able to trace the culprit of this cosmic antimatter shower, and it all comes down to another high-energy discovery. A strange gamma-ray haze named Geminga, first identified in the 1970s. What is this mysterious source of gamma radiation? And what does it have to do with the unusual abundance of high-energy positrons hitting our planet? I'm Alex McColgan, and you're watching Astrum. Join me today as we tune into the enigmatic frequency of Geminga, whose gamma radiation has lit up the world of astrophysics for decades. Up in our night sky, nestled in the Gemini constellation in the northern celestial hemisphere, there is something peculiar going on. In 1972, NASA's Small Astronomy Satellite 2, or SAS-2, identified an unknown source of gamma radiation. But with the technology available at the time, the best it could do was trace its origin to this wider region of our Milky Way. So, the radiation's ultimate source remained hidden among the stars for decades. Nevertheless, it was given a name, Geminga, as coined in 1976 by Italian physicist Giovanni Bignami, who would dedicate his career to studying it. It's a play on words, a combination of Gemini, the region where it's located, and gamma, the type of radiation it emits. Geminga is also a pun in Bignami's Milanese dialect, meaning it's not there, a fitting name for a gamma-ray haze with unknown origin. It wasn't until 1983 when Bignami and his team finally had their big break. They managed to identify a weak X-ray signal from Geminga using the Einstein X-ray satellite. This meant, although its exact position remained unknown, they could narrow down their search area and were getting closer to uncovering Geminga's hiding place. But it didn't answer the big question, what is it? As astronomers could still only offer vague guesses about the true nature of the source. That was until 1991, when they had another lucky break. Two separate missions identified radiation coming from Geminga, and they weren't constant signals, but pulses. The first of these discoveries was made with a German-built X-ray telescope known as ROSAT, short for Röntgen-Satellit, named after the German word for X-rays. ROSAT was the first to identify pulses in the X-ray signal coming from Geminga, and soon after, they were also confirmed in the gamma wavelengths
by the Energetic Gamma Ray Experiment Telescope, or EGRET, a telescope aboard NASA's Compton Gamma Ray Observatory satellite. Not only did these complementary observations demonstrate that the X-rays and the gamma rays were both coming from Geminga, but for the first time they revealed what Geminga was. With a period of 0.237 seconds, flashing as it spins around its axis a little more than 4 Hz, or 4 times per second, Geminga behaved like a pulsar. A pulsar is a type of neutron star that spins rapidly, emitting beams of radiation that sweep across space like a cosmic lighthouse. From across the galaxy, most pulsars appear to flash in radio waves, anywhere from a few times a minute to as fast as 700 times per second. And at this point in the early 90s, they were incredibly rare. You see, before ROSAT and EGRET, only 2 other high-energy gamma-ray pulsars had ever been identified, the Crab and Vela pulsars. And Crab and Vela were different to Geminga in a couple of key ways. First, in addition to gamma rays, both of these pulsars also produced radio waves, and were therefore visible using radio telescopes. So if Geminga was a pulsar, then it would be the first discovery of one that was apparently radio silent, only emitting enough radiation to be seen in the gamma and X-ray wavelengths. And second, Crab and Vela were surrounded by their respective nebulae, remnants from when they were created from supernova explosions. But Geminga's nebula was conspicuous by its absence. So why is Geminga, this powerful source of gamma rays, so good at hiding from our radio telescopes? Where is its nebula? Or could it be a different type of object altogether? Well, the answer to the first question is, in part, because we hadn't been listening properly, due to the limitations of the available technology and due to our understanding of the radio emissions of such stellar remnants. You see, while radio pulsars can emit radio waves across a wide bandwidth from as low as 17 MHz to above 87 GHz, around half the radio spectrum, not all of these frequencies travel well through space. Even though we've known since the 1970s that radio pulsars often peak between 100 to 200 MHz, where they are intrinsically brightest, things like the interstellar medium, background sky temperature, and effects from the ionosphere mean that lower frequencies are dampened as they make their way across space, resulting in very weak signals that are much more difficult to detect. Because those radio signals are so weak, most radio telescopes hadn't been looking for them, instead confining themselves to searching for signals between 430 and 1600 MHz. This would have been fine had Geminga behaved as expected for one of its kind. Since it did not, it took until 1997 for scientists to realize what was happening. 3 independent observations from the Pushina Radio Astronomy Observatory were able to identify extremely weak pulses from Geminga using a sensitive transit antenna. The faint radio pulses came in around 100 MHz, which explains why previous radio searches for Geminga had come up silent. Turns out, Geminga wasn't truly hiding and had been sending us signals. We just weren't listening correctly. That same year, a team led by the late astronomer Janusz Gill theorized that another reason Geminga had appeared to be radio silent may be its magnetic field. Models showed that radio waves may be absorbed or refracted within the pulsar's magnetosphere, leaving only weak pulses around 100 MHz to be detectable. This would effectively leave it quiet at the higher radio bands than most telescopes used. Confirming Geminga was a pulsar, and specifically a gamma-ray pulsar, was a big deal. In fact, 99% of its output is in the gamma range, making it one of the brightest gamma-ray sources in our entire galaxy. It is, as it turns out, all that's left after a star several times more massive than our Sun, exploded about 350,000 years ago. But its relative radio silence and its apparent lack of a nebula weren't the only unusual things about this pulsar. When Italian astrophysicists, including Bignami, Geminga's name-giver, compared a series of observations from the European Southern Observatory's 3.6 meter telescope and New Technology telescope with observations from the Canada-France-Hawaii telescope, they found that Geminga was moving. Not only that, it was traveling at an unusually high speed of around 0.2 arcseconds per year. As a reminder, an arcsecond is a very small unit of angular measurement, used when we need more precise measurements than a degree would allow. Within each arc degree, there are 60 arc minutes, and within each arc minute are 60 arc seconds. These arcseconds are a common unit used in astronomy to talk about the movement of objects across the sky from our perspective on Earth. If you were to draw a circle around the orbit of the Moon around the Earth, there would be 360 degrees around that circular path. So at any given time of day or night, assuming nothing is blocking your view of the horizon, you can see about 180 degrees of the sky. And from the horizon to the zenith, the top of the sky is 90 degrees. If you hold out your little finger at arm's length and close one eye, the tip of your little finger covers about 1 degree of the sky, roughly. Next time you're outside on a clear night, try this, and see if your little finger can cover the moon. It should, because the moon takes up only about half of a degree, or about 31 arc minutes in the night sky. Geminga traveling 0.2 arc seconds across our sky each year may not sound like a lot, but from our perspective on Earth, the typical star only moves a few thousandths of an arc second per year. Yet, despite being 800 light years from us, Geminga will travel 30 arc minutes, the equivalent to the apparent diameter of the Moon across our sky in just over 10,000 years. In other words, this stellar corpse is racing through the galaxy at nearly 210 kilometers per second. Heading towards the border between the constellations Gemini and Lynx, and at its current rate of motion, Geminga will remain in Gemini for another 500,000 years, but it may need a new name after that. However, this mysterious pulsar gets stranger still. It is its vast speed that helps produce another feature that scientists were about to discover. As it hurtles through space, Geminga leaves behind 2 ghostly X-ray tails that streak 3 trillion kilometers across the sky. As I discussed earlier, despite the fact that this fast-moving pulsar is nearly radio silent, it certainly isn't quiet in the gamma ray and X-ray wavelengths. In 1999, ESA's X-ray Multi-Mirror Mission, or XMM Newton, was launched to peer deeper into this X-ray universe, and 4 years later, a team led by Patricia Caraveo uncovered these comet-like X-ray trails. Their shape and brightness are partly explained by the shockwave created by Geminga's motion through space and its rotation as a pulsar, but they are also revealing of another attribute, Geminga's colossal mass. Measuring only about 20 to 30 kilometers across, Geminga is extremely dense, containing about as much mass as 1.5 of our suns. To put that in perspective, if you had a teaspoon of neutron star material, it would weigh about 4 billion tons, as much as 10,000 Empire State Buildings. As this dense, high-mass object races forward through the low-density interstellar medium, just 0.06 to 0.15 atoms per cubic centimeter, it compresses the interstellar medium and its own embedded magnetic field by a factor of 4. Meanwhile, the incessant spinning of the neutron star creates an environment where electrons and their antimatter counterparts called positrons, can be accelerated to extreme energies, powerful enough to emit high-energy gamma rays. While most of these electrons are seen in the gamma radiation that escapes from the pulsar, some get trapped and spiral within this enhanced magnetic field. In these images from a computer model, the tails can be seen streaking along the edges of Geminga's three-dimensional shockwave, like the wake created by a boat going through water. Only this boat is more massive than our Sun, and the wake is made up of extremely high-energy X-rays. But the final piece of the Geminga puzzle wasn't discovered until 2005. Its nebula. Taking the form of a shell of neutral hydrogen gas with a radius of 0.4 parsecs wide, it turned out to be what we call a pulsar wind nebula. This type of nebula is created from the wind plasma that emanates from a pulsar's magnetic poles. The plasma, made of charged particles that can be accelerated to near light speed, surrounds the pulsar, creating a nebula of high-energy particles that give off strong X-ray emissions. With the confirmation that Geminga did have a nebula, its identity as a pulsar could finally be confirmed. But Chandra went even further. In addition to imaging Geminga, Chandra also looked at a second pulsar called B0355+54, and by comparing the two, astronomers uncovered another possible explanation for the absence of radio pulses from Geminga. On the surface, these pulsars seem quite similar. They are both about 500,000 years old, and they spin about 4 to 5 times per second. However, as you know, Geminga is seen primarily in gamma ray pulses, with no bright radio emissions. By contrast, the other pulsar, which I'll refer to as pulsar B, is not seen in gamma rays, and instead is one of the brightest known radio pulsars. How could these two pulsars be so similar, yet so vastly different in how we see them? The answer may be as simple as how each of these pulsars are oriented relative to our observation from Earth. Astronomers believe that these images of Geminga and pulsar B have revealed their spin axes and uncovered a reason for why radio and gamma ray pulses may be present or absent on different pulsars. Like our own magnetic field around Earth, both of these pulsars have magnetic poles close to their spin poles. These poles are where the beams of pulsing radio emissions come from. You could try to model this if you skewer a little foam ball right down the middle. The foam ball is a pulsar, and the radio beams coming from the poles are represented by the wooden skewer coming out both ends. If you spin the ball around the skewer like a spin axis, you create an equator around the middle. To illustrate the gamma ray source along the spin equator, called the torus, you could cut a hole in a paper plate and squeeze it over the foam ball. Now you've got yourself a disk of gamma rays beaming out from the equator in every direction. With Geminga, the edge of the paper plate is pointing towards us, meaning the gamma rays are heading to Earth. But for pulsar B, its relative position to us is at a different angle, as if looking at the flat surface of the plate. The gamma rays are moving perpendicular to our line of sight, therefore missing Earth. Let's look again at the two Chandra images of Geminga on the left and pulsar B on the right, along with artist illustrations of what astronomers believe the pulsar wind nebulas look like for each of these. In the image of pulsar B, the long trailing blue tails represent the radio jets emanating from its poles, and the skewers coming out of both ends. Only instead of being straight like a wooden skewer, pulsar B is moving so fast through space that these jets appear bent backwards, trailing behind as the pulsar moves through space. Now look at the image of Geminga. Here, the long twin tails on either side of the image are the radio jets, trailing behind as it, too, rushes through space. But this time, instead of pointing almost directly toward and away from our vantage point on Earth, these jets appear to be coming off to the sides, not aimed at Earth. So when astronomers look at Geminga, They see powerful gamma ray emissions from the spin equator, but the radio jets point to the sides and remain unseen. And when they look at pulsar B, the opposite happens. The radio jets are pointed almost straight toward our planet, while the gamma ray source at the equator is missing Earth. Sometimes, the most simple explanation is the correct one. And that finally brings us back to the decades-long mystery of an unusual abundance of antimatter bombarding our planet. For more than a decade, a particle detector called the Alpha Magnetic Spectrometer, or AMS-2, has been attached to the International Space Station, collecting information on antimatter, dark matter, and cosmic ray sources. As a reminder, cosmic rays are energetic particles, fragments of atoms that travel through space at nearly the speed of light. These can be made by the sun, by supernova explosions, or other cosmic means. And in 2013, the first results of the AMS-2 experiment were announced. The detector had recorded more than 400,000 positrons, the largest sample of cosmic ray positron data ever collected, and increasing the world's total cosmic ray positron data by 100-fold. For years, many astronomers and physicists hoped that this excess antimatter may be the byproduct of a dark matter annihilation, offering possible clues about this mysterious substance. After all, dark matter could make up around 27% of the cosmos, and yet we still don't know what it is. Like regular matter, dark matter holds mass and takes up space, but it doesn't seem to absorb, reflect, or interact with light, at least not in a way we can detect. Some theorize that dark matter may be made of yet unidentified types of particles. Whatever it is, scientists had high hopes that the overabundance of antimatter being detected aboard the ISS may hold clues about dark matter's true nature. Unfortunately, they've been left disappointed. The more scientists dig into the data, the clearer it's becoming. The most likely source of these positrons may actually be pulsars. Astrophysicists had long suspected this, but until 2017, there simply wasn't proof. It was the High Altitude Water Cherenkov Gamma Ray Observatory that finally added evidence to this hypothesis. A small halo of gamma radiation was identified surrounding Geminga with trillions of times more energy than is visible to our eyes, from 5 to 40 trillion electron volts, the sort of radiation usually produced by positrons. This was the first real observational evidence pointing to a pulsar as a potential source. Pulsars naturally surround themselves with a haze of both electrons and their positron counterparts as a result of the star's intense magnetic field. This intense magnetic field pulls particles from the pulsar's surface and accelerates them to near the speed of light. Scientists think that these accelerated positrons and electrons are then colliding with starlight, boosting the light to higher energies, which then radiates as the gamma ray halo observed. But based on the size of the halo the Hawk team saw, Geminga's positrons would rarely have the energy required to reach our planet, and so they believed the excess positrons must have a more exotic source. That was until stunning new information was uncovered a few years later thanks to a team led by astrophysicist Matteo Di Maro. Using a decade of gamma ray data from Geminga acquired from Fermi's Large Area Telescope, which is able to observe lower energy light than the Hawk Gamma Ray Observatory, Di Maro's team was able to subtract out all other gamma ray sources to reveal a spectacular glow coming from Geminga, much, much bigger than what the scientists had ever seen before. The vast, oblong halo of glowing gamma rays at an energy of 10 billion electron volts spanned 20 degrees of the sky, similar to the area the Big Dipper constellation occupies. And that's not all. The glow of gamma radiation is even bigger at lower energies. If we could see it all with the naked eye, Geminga's gamma ray glow would dominate our sky, covering an area 40 times bigger than the full moon. With this new information, astrophysicists found that the size of Geminga's halo meant that this one pulsar alone could be responsible for as much as 20% of the excess positrons detected near Earth. From there, it's no stretch to imagine that other pulsars are the most likely culprit for the remaining antimatter abundance we found. This explanation may not have solved the mystery of dark matter, but it is certainly a magnificent revelation. It was Jocelyn Bell Burnell who discovered the first pulsar in 1967, back when people thought that those regular signals could be the work of extraterrestrial life. In the nearly 60 years that have passed since, we have found thousands of pulsars, and our understanding of these neutron stars has grown with every one. And since Geminga was identified as only the third known gamma-ray pulsar in 1991, we've now spotted over 300, thanks to NASA's Fermi mission. But given Geminga's track record of defying expectations and furthering science, I like to think that this particular pulsar has more secrets still to reveal. You may have noticed this video didn't have any sponsors, and that's because it was brought to you by our astronauts on Patreon. Consider joining our Patreon to keep these videos thriving, even when they're sponsor-free. It's the reason we can research deep into the topics we love, without cutting corners or chasing clicks. Every new astronaut allows us to explore bigger ideas, and make every upload even better than the last. So if you've ever thought about being a bigger part of this channel, join the crew to power Astrum and keep space curiosity alive.